Chapter 5, Exercise Numericals. 5.1, answer the following questions regarding Earth's magnetism. A vector needs three quantities for its specification. Name the three independent quantities conventionally used to specify Earth's magnetic field. So to specify Earth's magnetic field, we use three quantities. One, that is magnetic declination. Second one, that is angle of dip. And third one, that is horizontal component of Earth's magnetic field. B, the angle of dip at a location in southern India is about 18 degree. Would you expect a greater or smaller dip angle in Britain? Now, since Britain is closer to the magnetic North Pole, the angle of dip that would be greater. C, if you made a map of magnetic field lines at Melbourne in Australia, would the lines seem to go into the ground or come out of the ground? Since Australia is closer to the magnetic South Pole, hence magnetic field lines would come out of the ground. Okay. So D, in which direction would a compass free to move in the vertical plane point to if located right on the geomagnetic north or south pole? So at north or south pole, the magnetic field direction, that is vertical one. And now if you place a needle, then it will be stable in any direction, because vertically, upward or downward, in all the directions, the magnetic field lines are present. E, the Earth's field it is claimed roughly approximates the field due to a dipole of magnetic moment 8 into 10 raised to 22 joule per Tesla, located at its center. Check the order of magnitude of this number in some way. So we can use the formula for the magnetic field at any point on the equator of the dipole. So that is mu 0 m upon 4 pi r cube. In this particular equation, substitute m, magnetic moment, that is 8 into 10 raised to 22 joule per Tesla. And r, that is the radius of the earth, that is 6.4 into 10 raised to 6 meter, mu 0 upon 4 pi, that we can replace by 10 raised to minus 7. So in this equation of B, if we substitute all these values and then after if we solve it, our answer that will come to 0.3 into 10 raised to minus 4 Tesla. So we can say that is nearly equal to 0.3 Gauss. Clear? And this one is very close to the actual average value, that is 0.4 Gauss. Clear to all of you? F, geologist claims that beside the main magnetic poles, there are several local poles on the Earth's surface oriented in different directions. How is such a thing possible at all? Now, local poles may happen due to deposit of magnetized minerals, irons, etc. Right? Earth's poles are the total sum of approximately all such magnetic fields inside the surface and in its core. 5.3. A short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 raised to minus 2 joule. What is the magnitude of magnetic moment of the magnet? Very simple thing. Angle theta between the axis and the external field, that is given to you 30 degree. External magnetic field, that is 0.25 Tesla. tau, that is 4.5 into 10 raised to minus 2 joule. And what is the magnitude of magnetic moment that we want to find? Now, very simple. Torque acting on the magnetic moment placed in the uniform magnetic field B. We derived the equation in the theory, that is tau equal to mb sine theta. So m equal to tau upon b sine theta. Tau that is given to you 4.5 into 10 raised to minus 2. B that is given to you 0.25. Theta that is 30. So sine 30. Now solve this one. You will get the answer 0.35 ampere meter square. Clear? Point 4. A short bar magnet of magnetic moment M equal to 0.32 joule per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar is free to rotate in the plane of the field, which orientation would correspond to its stable and unstable equilibrium? What is the potential energy of the magnet in each case? Now, magnetic moment that is given to you 0.32 joule per Tesla. It is placed in the uniform magnetic field B, that is 0.15 Tesla. Now, which one is the position for stable equilibrium? So when the angle between magnetic moment and the external field that is equal to 0 means both are in the same direction, then that is the stable equilibrium. So we can write for theta equal to 0, we will get stable equilibrium. And in that particular situation, the potential energy, that is, now equation for the potential energy is minus mb cos theta. So minus m, that is 0.32 given to you, b 0.15 given to you, and for stable equilibrium theta that we have to take 0. So cos 0, that is 1. Now solve this one, you will get potential energy in stable equilibrium. Then after unstable equilibrium, so when the magnetic moment and the external field both are in mutually opposite direction, means theta, that is pi, that is unstable equilibrium. So in that particular case, the potential energy U dash, that is again minus mb cos theta. So minus m, that is 0.32, b that is 0.15 cos pi, right? So both the answers will be same one, but for stable equilibrium, the potential energy, that is minimum 1, that is with negative sign. And for unstable equilibrium, the potential energy will be maximum 1, that will be plus mb. Clear to all of you? 5.5. A closely wound solenoid of 800 tons and area of cross section 2.5 into 10 raised to minus 4 meter square carries a current of 3 ampere. Explain the sense in which the solenoid acts like a bar magnet. What is its associated magnetic moment? Now see, the solenoid given to you, that is with total number of tons 800, its area of cross section, that is 2.5 into 10 raised to minus 4 meter square, current passed through it, that is 3 ampere. Now when the current is passed through the solenoid, the magnetic field is produced by it, and the magnetic field lines of the solenoid are identical to the magnetic field lines of the bar magnet. So we can say solenoid itself behave as a magnet, and one end of solenoid that will behave as north pole, other end will behave as south pole. Now we have to calculate its magnetic moment. So magnetic moment M, that is NIA, and total number of turns that is given to you 800. The current passed through the solenoid I, that is 3 ampere, and area of cross section, that is 2.5 into 10 raised to minus 4. Solve this one, you will get the answer. Clear? 5.6. If the solenoid in exercise 5.5 is free to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of torque on the solenoid when its axis makes an angle of 30 degrees with the direction of applied field? So, magnetic field applied, that is 0.25 Tesla, and the angle between the axis of the solenoid and the external uniform magnetic field, that is 30 degrees. And here we can write the equation for the torque, that is mb sine theta. M that we have to take from the previous example, because the same solenoid which one is given to you in exercise 5.5 that we have to use here, and its magnetic moment that we calculated in the previous example. So that particular value we have to substitute here. B, that is 0.25 sine 30, and now solve this one, you will get the torque acting on that particular solenoid. Clear to all of you? 5.7. A bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. A. What is the amount of work required by an external torque to turn magnet so as to turn the magnet to align its magnetic moment normal to the field direction to opposite to the field direction? B. What is the torque on the magnet in cases 1 and 2? Now see, magnetic moment of the bar magnet that is given to you, 1.5 joule per Tesla, and the magnetic field that is of 0.22 Tesla. Okay, now we have the equation for the work done to rotate the bar magnet, or we can say magnetic moment in the magnetic field from angle theta 1 to theta 2. That is W equal to MB cos theta 1 minus cos theta 2. Okay. Now, initial position, that is aligned with the field, means theta 1, that is equal to 0. And from that particular position, say, so as to turn the magnet, so as to align its magnetic moment. So from theta 1 equal to 0 to theta 2 equal to 90, normal to the field direction. So we can write W1, that is M is 1.5, B that is 0.22, cos theta 1 that is cos 0, cos theta 2 that is cos 90. Now solve this one, you will get the answer. Then torque in that particular case, so tau 1 that is equal to mb sine theta 2. So m that is 1.5, b that is 0.22, sine theta that is sine 90. Again solve this one, you will get the answer. Clear? Now work done to rotate the magnetic moment, or we can say bar magnet, from the aligned position to opposite to the field direction. So theta 1 initial position, that is 0. Theta 2 days, the final position, that is 180 degree. So Work done. Again, we can use the same equation MB cos theta 1 minus cos theta 2. M that is 1.5, B that is 0.22. Cos 0 minus cos 180. Solve this one. You will get the work done. And now in that particular case, the torque acting on it, tau 2, that is MB sine theta 2 dash. So M that is 1.5, B that is 0.22, theta 2 that is pi, and sine pi that is 0. So torque in this particular case will be 0. Clear to all of you? 5.8. A closely wound solenoid of 2000 tons and area of cross section 1.6 into 10 raised to minus 4 meters square carrying a current of 4 ampere is suspended through its center, allowing it to turn in a horizontal plane. A. What is the magnetic moment associated with the solenoid? B. What is the force and torque on the solenoid if a uniform horizontal magnetic field of 7.5 into 10 raised to minus 2 Tesla is set up at an angle of 30 degree with the axis of the solenoid? Now see, first the given data, total number of turns in the solenoid, that is 2000, area of cross section, that is 1.6 into 10 raised to minus 4 meters square, current passed through it, that is I equal to 4 ampere, and first we have to calculate the magnetic moment associated with the solenoid. So M is what? Now in second question, the uniform magnetic field, that is 7.5 into 10 raised to minus 2 Tesla is applied, and the angle between the axis of the solenoid and the field theta, that is given to you 30 degree. Now what is the torque acting on the solenoid and what is the force acting on the solenoid, that we want to calculate. Clear to all of you? Now first the magnetic moment. So we have equation of it, NIA, N that is given to you 2000, I that is 4 ampere, area of cross section, that is 1.6 into 10 raised to minus 4. Solve this one, you will get the answer of magnetic moment. Then torque acting on it, that is tau equal to MB sine theta. Substitute this calculated value of M here. Then B that is given to you 7.5 into 10 raised to minus 2. Theta that is 30, so sine 30 degree. Solve it, you will get the answer. Then force. Now we know this thing, when any coil is placed in the uniform magnetic field, the net force acts on it, that is equal to 0. Or we can say when any magnetic moment is placed in the uniform magnetic field, the net force acts on it, that is 0. Because the north pole and south pole of that magnetic moment will experience the forces in mutually opposite direction in external field, and these forces will be equal in magnitude. Therefore, net force will be 0. Clear to all of you? 5.9. A circular coil of 16 turns and radius 10 centimeter carrying a current of 0.75 ampere raised with its plane normal to an external field of magnitude 5 into 10 raised to minus 2 Tesla. The coil is free to turn about an axis in its plane perpendicular to the field direction. When the coil is turned slightly and released, its it oscillates about its stable equilibrium with a frequency of 2 second inverse. What is the moment of inertia of the coil about its axis of rotation? Again, very simple example. See, the given data, that is total number of turns 16, then R radius, that is 10 centimeter, so 0.1 meter. The current through it, that is 0.75 ampere. It is placed in the magnetic field of magnitude 5 into 10 raised to minus 2 Tesla, and it oscillates with frequency 2 second inverse. Now, first of all, we have to calculate magnetic moment. Magnetic moment M, that is NIA. Area is not given to you, but radius is given to you. So magnetic moment, that is Ni into area, that is pi r square. N number of turns 16, I, that is 0.75 ampere, pi 3.14, radius 0.1, take square of it, and now solve this one, you will get magnetic moment. Now we want to calculate moment of inertia. So we have the equation for the frequency of oscillations, that is 1 upon 2 pi under root mb upon I. Take square on both the side. So f square, that is 1 upon 4 pi square mb upon I. Make I as a subject of equation. So I, that is equal to 1 upon 4 pi square mb upon f square. Now substitute the value of m, which we calculated here. Then b, that is given to you 5 into 10 raised to minus 2 Tesla upon 4 pi square, that is 3.14 square, f square, f that is given to you 2, so 2 square, and now solve this one, you will get the answer kilogram meter square. Clear to all of you? 5.10. A magnetic needle free to rotate in a vertical plane parallel to the magnetic meridian has its north tip pointing down at 22° with the horizontal. The horizontal component of the Earth's magnetic field at the place is known to be 0.35 Gauss. Determine the magnitude of the Earth's magnetic field at the place. Simple. The angle of dip or inclination that is given to you, I equal to 22°. Horizontal component of Earth's magnetic field, that is 0.35 Gauss, that is also given to you. We have to calculate Earth's magnetic field at that place, BE. Now we have the relationship horizontal component of Earth's magnetic field, that is BE cos I. So BE, that is HE upon cos I, HE, that is 0.35 upon cos 22. Now here we have to substitute the value of cos 22° from the log table and then solve it. You will get the answer in Gauss. Then multiply it by 10 raised to minus 4. You will get the answer in terms of Tesla. Clear to all of you? 11. At a certain location in Africa, a compass points 12° west of the geographic north. The north tip of the magnetic needle of a deep circle placed in the plane of magnetic meridian points 60° above the horizontal. The horizontal component of Earth's magnetic field is measured to be 0.16 Gauss. Specify the direction and magnitude of the Earth's field at the location. Again, simple thing, the angle of dip or inclination that is given to you 60°. Then horizontal component of Earth's magnetic field 0.16 Gauss, and you have to calculate BE. So again the equation HE, that is BE cos I, So BE, that is HE cos I. HE, that is 0.16 upon cos 60. Solve this one, you will get magnetic field in terms of Gauss. Then multiply it by 10 raised to minus 4. You will get answer in Tesla. So this is the magnitude of the magnetic field. And for direction, you have to write the same thing, this one. Direction of the magnetic field, that is at 60 degree above the horizontal direction. Clear to all of you? 5.12. A short bar magnet has a magnetic moment of 0.48 joule per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance of 10 centimeter from the center of the magnet on A, the axis, B, the equatorial lines of the magnet. Now see, magnetic moment that is given to you 0.48 joule per Tesla. And the point is at a distance r equal to 10 centimeter, means 0.1 meter, where we want to find the magnetic field. Now, first we have to calculate the magnetic field at a point on the equator as well as at a point on the axis of the dipole moment. Now, B axial, that is mu 0 upon 4 pi 2m upon r cube equation we derived in the theory. Mu 0 upon 4 pi, that is 10 raised to minus 7, to m, that is 0.48 upon r, that is 0.1 cube. Solve this one, you will get the magnetic field at axial point. Now equatorial. So B equatorial, that is mu 0 upon 4 pi m upon r cube. So if the position of the point is the same on the axis as well as on the equator, means r is the same, then we can see B equatorial, that is half, then B axial. So whatever is the answer here of B axial, divide it by 2, you will get the magnetic field at the same distance 10 centimeter on the equatorial line. Clear to all of you? 5.13. A short bar magnet placed in a horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 centimeter from the center of the magnet. The Earth's magnetic field at the place is 0.36 Gauss and the angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point? It implies at 14 centimeter from the center of the magnet. At null point, field due to the magnet is equal and opposite to the horizontal component of Earth's magnetic field. Now, say, short bar magnet is placed in a horizontal plane. Axis aligned along the magnetic north-south direction. Okay, so this one is north pole of the external magnetic field. This one is the south pole of external magnetic field. And null point is found on the axis of the magnet. So if the magnet is placed in such a way, the north pole of the magnet is towards the north and south pole of the magnet is towards the south of external field. Then the magnetic field of your magnet on its axis, that will be in the direction of its dipole moment, south to north. So in this particular direction, right? Which one is represented here by this blue arrow. An external field that is in the opposite direction. Then and then only you will get the null point on the axis of the bar magnet. Clear this concept? Here, if the north pole of the magnet is towards the north of external field and south of the magnet is towards the south of the external magnetic field, then and then only the null point will be on the axis. And on equatorial line, you will never get the null point. But if the magnet is in the opposite direction than shown in this figure, then null point will be obtained only on the equatorial line. You will never get the null point on the axis of the magnet. Now see, the distance that is given to you for the point R, that is 14 centimeters, so 0.14 meter. The horizontal magnetic field of Earth, that is 0.36 Gauss, that is 0.36 into 10 raised to minus 4 Tesla. Now, you are getting null point at 14 centimeter on the axis. It implies that the magnetic field on the axis at that point, that is exactly equal to Earth's magnetic field magnitude wise, and both are opposite that we discussed in the figure. So we can write Bx is equal to mu 0 upon 4 pi 2m upon r cube, that is on axis. Now He 0.36 into 10 raised to minus 4, that is equal to mu 0 upon 4 pi, that is 10 raised to minus 7, 2 m upon 0.14 cube. Now solve this one, you will get m. Now at the same position, the magnetic field on the equator, so we know the total magnetic field at the same point on the equator. So at equator, B equatorial, that is B axial by 2. This one is due to magnet. B axial, that is equal to He. Here we discussed. So B equatorial, that is He by 2. So this is the magnetic field of bar magnet. But we want to find the total field. So total field, that is B equatorial plus Earth horizontal is already there. But here we proved B equatorial, that is He by 2. So here if we substitute He by 2, then resultantly we will get 3 by 2 He. Now here substitute the value of He, that is given to you 0.36 into 10 raised to minus 4 Tesla. Then solve it, you will get the total field. Now see here, without calculating this thing directly, you can solve the problem in this way. But why here this equation I placed? Because suppose it is asked to you not exactly at the same point, but at some other point, if you want to calculate the resultant or the total field, then in that particular case, you require m. And then you have to substitute the value of m in the equation of B equatorial. And they can ask you additionally to calculate the magnetic moment also in this case. And therefore, this portion is mentioned here. Clear to all of you? 5.14. If the bar magnet in exercise 5.13 is turned around by 180 degree, where will the new null points be located? New null points will be located on the equatorial line. Because see, for the bar magnet, the external field that is from north to south, and horizontal field that is represented here. So external field that is north to south. So on left hand side here, there is the north of Earth's field, and on right hand side here, south will be there. Now see, at any point on the equatorial line, this one, the magnetic field of the bar magnet that is towards left, and horizontal magnetic field of Earth that is towards right. It implies that at each and every point on the equatorial line, both field will be mutually opposite. So the point where magnitude wise both becomes equal, there you will get null point. Clear to all of you? So now for the null point on equator, both the fields, the field of bar magnet and the horizontal magnetic field of Earth, both should be equal in magnitude, opposite in direction. So are opposite in direction that we discussed. So now we have to take their magnitudes equal. So B equatorial, that should be equal to horizontal Earth's magnetic field. So we can write that is equal to mu 0 upon 4 pi m upon r cube. Now we already discussed B axis, that is mu 0 upon 4 pi 2m upon r axis cube, and that is also equal to He. Now here for this He, if we substitute this particular equation, or in other words, we can say we can compare these two. So mu 0 upon 4 pi m upon r equator cube, that is equal to mu 0 upon 4 pi 2m upon r axis cube. So r equatorial cube, that is equal to r axis cube upon 2 raised constants are cancelled. So r equatorial, that is r axis upon 2 raised to 1/3. And in previous example, the null point was obtained at 14 centimeter on axis. So r axis is replaced by 14 upon 2 raised to 1/3. Solve this one, you will get the answer. Clear to all of you? And you can solve this one by calculating the magnetic moment in the previous example, and then after by substituting the value of magnetic moment mu 0 upon 4 pi and He in this equation, and then calculate R. Clear to all of you? 15. A short bar magnet of magnetic moment 5.25 into 10 raised to minus 2 joule per Tesla is placed with its axis perpendicular to the Earth's field direction. At what distance from the center of the magnet? The resultant field is inclined at 45 degree with Earth's field on A, its normal bisector, and B, its axis. Magnitude of Earth's field at the place is given to be 0.42 Gauss. Ignore the length of the magnet in comparison to the distances involved. First of all, you have to understand the question itself. Okay. Say the horizontal Earth's magnetic field that is given to you 0.42 Gauss. Magnetic moment of bar magnet, that is 5.25 into 10 raised to minus 2 joule per Tesla. Okay. Now the bar magnet with its axis perpendicular to the Earth's field direction. In that way it is placed. See, this is the axis of the bar magnet, and this is Earth's horizontal magnetic field. Both are perpendicular to each other. Now, here the resultant field is inclined at 45° with Earth's field on its normal bisector. So this is the normal bisector of bar magnet. Now, suppose at this particular point, the resultant magnetic field B, resultant that is of two fields, one field that is of bar magnet and second field that is of Earth, and resultant of these two that is denoted here by B. So this B that is at 45° with Earth field. Now, if magnetic field B is exactly at 45 with He, then it is possible only when He and B equatorial both becomes equal. Then here this will be 45. Or we can prove it mathematically also. If this angle between B and He that is 45, then you can write tan 45 that is B equator upon He. Tan 45 is 1. So B equator and He that is same. So B equator that is equal to He, and that is equal to, we can write mu 0 upon 4 pi m upon r equator cube. He 0.42 into 10 raised to minus 4, mu 0 upon 4 pi that is 10 raised to minus 7, m that is 5.25 into 10 raised to minus 2 upon r equator cube. Now solve this equation and from that calculate r equator, means at this particular distance you will get the resultant magnetic field exactly at 45° with Earth's horizontal field. Clear up to this one? Now, in the similar way, we have to find the position on the axis where the resultant magnetic field that is at 45° with Earth's horizontal field. So see, suppose at this particular point, the resultant magnetic field that is at 45° with He. So again, this one is possible only when He and B axial both becomes equal. So we can write here B axial that is equal to He, that is mu 0 upon 4 pi 2m upon r axial cube. So He 0.42 into 10 raised to minus 4 mu 0 upon 4 pi 10 raised to minus 7 to m that is 5.25 into 10 raised to minus 2 upon r axis cube. Solve this one and now calculate r axis, means at this much meter from the center of the magnet on the axis, the resultant magnetic field that will be exactly at 45° with Earth's horizontal field. Clear to all of you? Additional exercise. Now this one is theoretical. Example A. Why does a paramagnetic sample display greater magnetization for the same magnetizing field when cooled? So When it is cooled, then as per Curie's law, its magnetization increases because magnetization inversely proportional to temperature. And as the temperature decreases, its randomization also decreases because thermal energy associated with it decreases. B. Why is diamagnetism in contrast almost independent of temperature? Because in diamagnetic, the molecular dipole moment always align in the opposite direction of the external magnetizing field. C. If a toroid used bismuth for its core, will the field in the core be slightly greater or slightly less than when the core is empty? So bismuth, that is diamagnetic substance. The list is given to you in the text. So if we use bismuth as a core of toroid, then we know for diamagnetic substance, when it is placed in the external field, inside it the magnetic field decreases. So slightly less than when the core is empty. Clear up to this one? Is the permeability of a ferromagnetic material is independent of the magnetic field? If not, is it more or lower or more for lower or higher fields? No, the permeability of the ferromagnetic material is not independent of the magnetic field. It is more at higher field, it directly proportional to the field. E. Magnetic field lines are always nearly normal to the surface of a ferromagnetic at every point. This fact is analogous to the static electric field lines being normal to the surface of a conductor at every point. Why? As the magnetic permeability of a ferromagnetic, that is too much large than the unity. So magnetic field lines are always nearly normal to the surface of the ferromagnetic substance. F. Would the maximum possible magnetization of a paramagnetic sample be of the same order of magnitude as the magnetization of the ferromagnetic? Yes, but for the maximum possible magnetization of paramagnetic sample, impractically very high magnetizing fields are required. Clear? 5.17. This one is also theoretical one. Answer the following questions. A. Explain qualitatively on the basis of domain picture the irreversibility in the magnetization curve of a ferromagnetic. Now see, for ferromagnetic substance, when we magnetize it and demagnetize it, so in that particular case, we will get the magnetization curve. That is the hysteresis curve. But during the magnetization and the demagnetization, the loss of energy in the form of heat that takes place. Okay. So the energy which one is utilized to magnetize it, the same energy that will not be obtained during its demagnetization. And therefore, you will not get the reversible curve for it. And that particular loss of energy in the form of heat that can be calculated with the area enclosed by that hysteresis loop. Clear? B. The hysteresis loop of a soft iron piece has much smaller area than that of a carbon steel piece. If the material is to go through repeated cycles of magnetization, which piece will dissipate greater heat energy? Obvious, carbon steel piece, because here it is given to you the hysteresis loop of the soft iron has a smaller area than carbon steel, and the area enclosed by the hysteresis loop that give you the loss of energy in the form of heat. C. A system displaying a hysteresis loop such as a ferromagnetic is a device for storing memory. Explain the meaning of this statement. So magnetization of the ferromagnetic is not a single value for a particular field. Depends both on the magnetizing field and on the history of magnetization. It implies that how many cycles of magnetization it has gone through. So the value of magnetization is a record or memory of its cycles in magnetization. If information bits can be made to correspond to these particular cycles, the system displaying such a hysteresis loop can act as a device for storing information. Now D, what kind of ferromagnetic material is used for coating magnetic tapes in a cassette player or for building memory stores in a modern computer? So ferrites or ceramics, which is specially treated barium iron oxides, are used for that. E. A certain region of space is to be shielded from magnetic fields. Suggest a method. Simple thing. By surrounding the region with soft iron rings, as magnetic field lines will be drawn into the rings and the enclosed space becomes free of magnetic field. So in this way, you can shield any certain region from the magnetic field. Clear? 5.18. A long straight horizontal cable carries a current of 2.5 ampere in the direction 10° north of east. The magnetic meridian of the place happens to be 10° west of the geographic meridian. The Earth's magnetic field at the location is 0.33 Gauss, and the angle of dip is 0. Locate the line of neutral points. Ignore the thickness of the cable. At neutral points, magnetic field due to the current carrying cable is equal and opposite to the horizontal component of Earth's magnetic field. So see, as per given data and this figure, you can understand this thing. The current carrying cable is exactly perpendicular to the magnetic meridian. Okay. Now see, we have to find the line of neutral points. So at neutral points, the magnetic field produced by this current carrying cable and the horizontal Earth's magnetic field both should be equal in magnitude, opposite in direction. So BH, that is equal to mu 0 I upon 2 pi r, that is equal to B. Clear? Means magnetic field of current carrying conductor and horizontal Earth's magnetic field, that should be equal in magnitude. Now R that is equal to mu 0 upon 4 pi I into 2 upon BH. Okay, to make here 2 pi to 4 pi, it is multiplied by and divided by 2. Now, this particular point that will be above the cable. How? Say, if this one is your cable and see in the cable, the current is flowing in this direction. Okay. So, if we hold this cable in the right hand like this, thumb is in the direction of the current. So, field line is coming out from upper side and going inside from the downward side. Now, here at upper side, when the field line is coming out like this, means the tangent that is perpendicular to the plane in outward direction. Now see, Earth's horizontal field that is in the opposite direction. Here, this one is geographic south. So here, magnetic north. From this side, the field lines comes out and it move towards this side. So its magnetic field that is in this direction, cable's magnetic field that is in opposite direction. Therefore, the null point that will be obtained in this upper side. Okay. Now substitute the values. Mu 0 upon 4 pi, that is 10 raised to minus 7, I 2.5, 2, and Earth's horizontal field that is 0.33 Gauss, that is 0.33 into 10 raised to minus 4. You will get the answer. Clear to all of you? 5.19. A telephone cable at a place has 4 long straight horizontal wire carrying a current of 1 ampere in the same direction east to west. The Earth's magnetic field at the plane is 0.39 Gauss. An angle of dip is 35 degree. The magnetic declination is nearly 0. What are the resultant magnetic fields at 0.4 centimeter below the cable? Now see, the current that is 1 ampere, magnetic field of Earth that is 0.39 Gauss, that is 0.39 into 10 raised to minus 4 Tesla. Angle of dip or inclination that is 35 degree. The point that we have to take 4 centimeter from the cable and we have to take it below the cable. So that is 4 into 10 raised to minus 2 meter. Now, horizontal component of Earth's magnetic field that is B cos IC here. Earth's resultant field is given to you, not horizontal component. So first of all, horizontal component that is B cos I. 0.39 into 10 raised to minus 4 cos 35, solve it, you will get answer 0.32 into 10 raised to minus 4 Tesla. Now from that calculate vertical component also. So B sin I, 0.39 into 10 raised to minus 4 into sin 35, solve it, you will get 0.22 into 10 raised to minus 4 Tesla. Now magnetic field of cable. So B cable that is mu 0 I upon 2 pi r. So mu 0 upon 4 pi 2 I upon r we can take. So mu 0 upon 4 pi 10 raised to minus 7 into 2 into current that is 1 ampere. Okay. Upon 4 into 10 raised to minus 2, solve it, you will get 0.2 into 10 raised to minus 4 Tesla. Now, resultant magnetic field that we want to calculate. East, west, north, south. current that is in this direction. So if we hold it like this, below the cable, the magnetic field due to cable that is in this direction. Earth's horizontal field that is from geographic south to north. It implies that below the cable, Earth's horizontal field and the field produced by cable both are in mutually opposite direction. So resultant field due to this Earth's horizontal component and cable's field that we can write as BH minus B cable, because both are exactly in opposite direction. At the same point, there is the vertical component of Earth's magnetic field. It implies that this BH minus B cable, that is the resultant field in horizontal direction, and vertical field is BB. These two are perpendicular to each other. Therefore, now we can write the resultant field B, that is under root resultant horizontal field BH minus B cable square plus BV square. Now we have to substitute the value BH, that is 0.32 into 10 raised to minus 4. B cable, that is 0.2 into 10 raised to minus 4. BV, that is 0.22 into 10 raised to minus 4, and then solve it, you will get the answer. Clear to all of you? 5.20. A compass needle free to turn in a horizontal plane is placed at the center of the circular coil of 30 tons and radius 12 centimeter. The coil is in a vertical plane making an angle of 45 degree with the magnetic meridian. When the current in the coil is 0.35 ampere, the needle points west to east. A. Determine the horizontal component of Earth's magnetic field at the location. B. The current in the coil is reversed and the coil is rotated about its vertical axis by an angle of 90 degree in anti-clockwise sense, looking from above. Predict the direction of the needle. Take the magnetic declination at the places to 0. Now see, the total number of turns in the coil that is given to you 30, the radius of the coil that is 12 centimeters, so 0.12 meter, and the current passed through it that is 0.35 ampere. Now the magnetic field produced by the coil at its center, that will be along the axis of it, and that is B equal to mu 0 I N upon 2R. Now magnetic field produced by the coil that is along the axis means it is perpendicular to the plane of the coil, and the plane of the coil that is at 45 degree with the magnetic meridian. So we can say now B is inclined to BH by 135 degree, and the resultant magnetic field is at 90 degree with BH because it is given to you the needle points west to east. Needle always align in the direction of resultant field, and Earth's horizontal field that is in north-south direction, your needle that is east-west direction, so are 90 degree with respect to each other. Now in standard 11th we studied about the parallelogram formula. So tan alpha that is the angle made by the resultant field with respect to the field B. So tan alpha here, alpha that is 90, that is equal to B sine theta, theta that is the angle between B and BH, means both the fields, okay, upon BH plus B cos 135. Now tan 90 that is infinite, okay. So B sine 135 that you can write B sine 45 upon BH B cos 135 that you can write minus cos 45, because you can write here cos 180 minus 135. Clear? So that is in the second quadrant. In second quadrant, cosine is negative. So minus cos 45. Now this one is equal to infinite, means this denominator that should be equal to 0. So BH minus B cos 45 that is equal to 0. So we can write BH equal to B cos 45. But B, that is the magnetic field produced by the current carrying coil. That is mu 0 In upon 2R into cos 45. So mu 0 that is 4 pi into 10 raised to minus 7. I that is 0.35, number of turns 30, cos 45 that is 0.707 upon 2 into 0.12. Solve this one, you will get the horizontal Earth's magnetic field, that is 0.388 Gauss. Clear to all of you? Then question B, when the current is reversed and the coil rotated by 90 degree, resultant field that is also reversed, it points east to west. Initially the needle was pointing west to east. So now it will point east to west. So the needle will also stay in the same direction.